When humans die, it's usually without fanfare. However, when stars go out, they do so in spectacular fashion, announcing their demise as loudly and brightly as possible. Star explosions are truly mind-blowing but terrifying events, and although not so common, the universe is serving us the spectacle of an exploding star this year. Which star is exploding? Can you watch the explosion? But more importantly, is the Earth in danger of an exploding star? Join us as we bring you everything about the terrifying star explosion that's happening in 2022. Stars live billions of years but haven't cracked immortality, so they eventually die. Some will burn out instead of fading and end up in huge explosions known as supernovae. Many stars cool in later life to end their days as white dwarfs and later become black dwarfs. When the few that become supernovae explode, they expel matter into space at about 9,000 to 25,000 miles or 15,000 to 40,000 kilometers per second. This type of blast is responsible for much of the material in the universe, including some elements like iron, which make up our planet and even your body. Yes, heavy elements in the universe can only come from supernovae, so all of us carry the remnants of these distant explosions within our own bodies. The end result of supernovae is adding enriching elements to space clouds of dust and gas, further into stellar diversity. However, the death of one star may be the birth of another because a supernova produces shockwaves that compress clouds of gas to aid new star formation. So how do supernovae work? The process starts when a star runs out of fuel. It needs fuel to sustain the fusion process taking place at its core. The thing is that star fusion provides a constant outward pressure, which exists in balance with the star's own mass-driven inward gravitational pull. However, when it slows down, the outbound pressure drops and the core starts to condense under gravity. That is, it becomes less dense and hotter. Ironically, to an observer, the star begins to grow, swelling into bodies known as red supergiants. However, the core stays shrinking, signaling an imminent supernova. When a star's core contracts to a critical point, a series of nuclear reactions is unleashed. This fusion staves off core collapse for a time, but it can only try because when the core becomes composed of mainly iron, it can no longer sustain star fusion. In a microsecond, the core may reach temperatures of billions of degrees Celsius. The iron atoms become so crushed so closely together that the repulsive forces of their nuclei create a recoil of the squeezed core. The bouncing effect causes the star to explode as a supernova and give birth to an enormous, superheated shockwave. Smaller stars are not completely immune to supernovae. Smaller stars, which may be as large as 8 times the mass of our own sun, usually evolve into white dwarfs. This means the star is condensed to about the size of the Earth, is very dense, and thus has a strong enough gravitational pull to gather material from a second star if it is close enough. If such a white dwarf pulls enough mass, it reaches a level called the Chandrasekhar limit. The pressure at its center will become so great that runaway fusion occurs and the star detonates in a thermonuclear supernova. A supernova is a prolonged event. It can light the sky up for weeks, and the massive transfer of matter and energy leaves behind a very different star. And when the process is complete, typically only a tiny core of neutrons, a spinning neutron star, is left as evidence. The resulting neutron star gives off radio waves in a steady stream or as pulsars in intermittent bursts. However, if the star is as massive as at least 10 times the size of our Sun, this is large enough to leave behind a large core. When this happens, a new phenomenon will occur. Because such a burned-out core has no energy source to fuse and thus produces no outward pressure, it may become engulfed by its own gravity and turn into a cosmic sinkhole for energy and matter, known as a black hole. Let's come back to our Sun. Can it go supernova on us? The Sun has enough fuel to last 10 billion years, and if it were to go supernova, there is no hope for the Earth. We are too close for comfort. However, thankfully the Sun is not massive enough to become a supernova despite its size. Now that we know our Sun will not go supernova on us, how much energy is produced during a Type 2 supernova? The unit of measure of this type of stupendous energy is FOE, meaning 10 followed by 51 zeros. During the Sun's lifetime, it will emit approximately 1.2 FOE of energy. However, a Type 2 supernova produces that in a few seconds. The second type of supernovas is Type 1a. This happens in a binary star system where one of the stars is a white dwarf, and the other is a companion star from which the white dwarf is busy stealing matter. Yes, theft happens in space too. A white dwarf is the superdense remnant of a smaller star which is about 8 times the mass of the Sun in the last phase of its life. It is the result of the slow shrinkage over millions of years of a red giant star, such as Betelgeuse in the constellation Orion, recently the subject of much speculation that it was about to go supernova. And a red giant star, in turn, is the result of a star like our own Sun slowly swelling up over millions of years when it begins to exhaust its supply of hydrogen. A white dwarf star is so dense that a teaspoonful of its material would weigh about 15 tons. In its interior, all nuclear fusion processes have ceased. However, they can be reignited. If the white dwarf acquires enough material to end up with more than 1.44 times the mass of our Sun, the processes can restart and lead to a runaway thermonuclear explosion and subsequent destruction of the white dwarf or a supernova. 2022 is a special year in cosmic history because scientists have predicted we might witness the full glory of an exploding star. The best part is that a piece of sophisticated equipment is not needed to track it because it will be visible to the naked eye in most parts of the world. What is even more special is that the type of explosion that will occur in 2022 is very rare. 2 stars will collide and nobody has ever witnessed this phenomenon. As reported in a study from a team of researchers from Calvin College in Grand Rapids, Michigan, a binary star system will likely merge, causing a massive explosion. As such, scientists are looking forward to this rare chance to study this kind of explosion. It will cause a light outburst so bright that it will become the brightest object in the night sky. A binary star means 2 stars that orbit one another and are so close that they share an atmosphere. Watching the stellar system will offer valuable clues to the ways stars live and die, or perhaps point to some still mysterious force that can perturb the orbits of stars. Meanwhile, scientists have been able to watch the explosion of a star in real time, and it made them conclude that supernovas may even be way more violent than we assumed. That was actually the first time we would witness a supernova taking place. Scientists began watching the ailing red supergiant named SN 2020 TLF more than 100 days before it finally died. The star was located about 120 million light-years from Earth, meaning the death took place about 120 million years ago, but we are just getting the memo. However, during the lead-up, the researchers saw the star erupt with bright flashes of light as great globs of gas exploded out of the star's surface. Stars don't get larger than red supergiants in the universe in terms of volume. They can measure hundreds or sometimes more than 1,000 times the radius of the Sun. However, they are only the bulkiest, but they are not the brightest nor the most massive stars out there. Supergiants like our Sun produce energy through nuclear fusion of elements in their cores. However, there is a difference. Because they are so big, red supergiants can forge much heavier elements than the hydrogen and helium that our Sun consumes as fuel. As supergiants burn even more massive elements, their cores become hotter and more pressurized, and by the time they start fusing iron and nickel, these stars run out of energy, their cores collapse, and they eject their gassy outer atmospheres into space in a violent Type II supernova explosion. Supergiants were nothing new to scientists actually. They had studied them before they went supernova. They had also studied the aftermath of explosions. What they were not able to study was the supernova event itself. But that changed when they began monitoring SN 2020 TLF in the summer of 2020. At the time, the star was flickering with bright flashes of radiation that the team later interpreted as gas exploding off the star's surface. With the help of 2 telescopes in Hawaii, the University of Hawaii Institute for Astronomy Pan-STARRS 1 telescope and the W.M. Keck Observatory on Mauna Kea, the researchers followed the cranky star for 130 days. The climax came when, at the end of that period, the star went boom. The team reported evidence of a dense cloud of gas surrounding the star at the time of its explosion, likely the same gas that the star ejected during the prior months. This suggests that the star started experiencing violent explosions well before its core collapsed in the fall of 2020. The observations led the scientists to the conclusion that red supergiants undergo significant changes in their internal structures, resulting in chaotic explosions of gas in their final months before collapsing. The first recorded case of a supernova was observed by the Chinese, recorded in the year 1054 CE. However, the supernova had occurred 6,523 years earlier because this star was that many light years away. However, we do see supernova remnants, expanding clouds in space where stars used to be. There are many examples of these clouds both inside and outside our galaxy. The most famous supernova remnant visible from the northern hemisphere is the Crab Nebula. It's located in the direction of the constellation Taurus the Bull. The Crab Nebula is famous for containing the first known pulsar, discovered in 1967 by Jocelyn Bell Burnell. As it is known, the Crab pulsar is a neutron star or the remnant of the supernova that created the Crab Nebula. Like cosmic lighthouses, pulsars give off beams of radio waves as they spin. The binary system predicted to merge in 2022 is the KIC 9832227. The team of researchers led by Professor Molnar has been observing this binary star system since 2013. Molnar got interested in KIC 9832227 when findings of its brightness changes were published. It led to questions about the nature of this star system. Molnar wanted to know whether it was a pulsar or a binary pair. Prior to the increased attention on KIC 9832227, astronomers didn't even know that the twinkling point of light was more than one star. But based on the timing and depth of those periodic eclipses, astronomers determined that one of the binary stars is about 40% larger than the Sun, while the other is just 1/3 the Sun's size. But as they rotate around each other, each one briefly blots out the other from the perspective of an observer from the Earth. After conducting their own observations using the Kelvin Observatory, Professor Molnar and his colleagues realized KIC 9832227 was what is known as a contact binary. This means it was a kind of binary star where the two stars are close enough to share an atmosphere. It is similar to the binary system known as V1309 Scorpii. V1309 Scorpii's stars shared an atmosphere and their orbit continued to decrease until they smashed into each other, causing a massive explosion and becoming a single star. Molnar's team expected the same fate to befall KIC 9832227, causing them to concentrate on the binary star system. KIC 9832227 is about 1,800 light-years away. If the merger event is anything like the 2008 explosion, it'll take about 6 months to rise to its full brightness, which is about 10,000 times greater than the brightness of the original. So to the big question, even though the Sun will not end up as a supernova, can the Earth ever be in danger from a supernova? First, what happens if the Earth were to suffer from the effect of a supernova? That depends on the distance of the explosion from the Earth. Let's say the supernova is about 30 light-years away from Earth. In that case, we would expect significant effects on the Earth, possibly mass extinctions. X-rays and more energetic gamma rays from the supernova could destroy the ozone layer that protects us from solar ultraviolet rays. It could ionize nitrogen and oxygen in the atmosphere, leading to the formation of large amounts of smog-like nitrous oxide. If the distance is less than 30 light-years away, you can kiss goodbye to the phytoplankton, and reef communities would be particularly affected. Such an event would severely deplete the base of the ocean food chain, and because these organisms form the basis of oxygen production on Earth and the marine food chain, any significant disruption to them could cascade into a planet-wide problem. We will be showered with gamma rays and other high-energy radiation. This radiation could cause mutations in earthly life. Also, the radiation from a nearby supernova could change our climate. Fortunately for us, there are no stars within 50 light-years of the Earth that can go supernova. In fact, no supernova has been known to erupt within 50 light-years in the known history of humankind. The most recent supernova visible to the eye was supernova 1987A in 1987. It was approximately 168,000 light-years away, far away enough to just be a spectacle in the sky and not affect our existence in any way. Before that, the last supernova visible to the eye was documented by Johannes Kepler in 1604. At about 20,000 light-years, it shone more brightly than any star in the night sky. It was even visible in daylight, but it didn't cause earthly effects. Now, the star explosion expected in 2022 is not something you want to miss, but how can you watch it? Luckily, it's very easy. Molnar assures amateur astronomers that they can track KIC 9832227's orbital timing and variations in brightness. But they won't be the only one that would enjoy the spectacle of the exploding star in 2022, because you won't need any special equipment to do so. This is a once-in-a-lifetime event, so it is okay to get excited about it. Just keep gazing in the northern hemisphere. Molnar & Co. have continued to monitor KIC 9832227 pending its explosion. This they have done with the help of the NROA's Very Large Array VLA, NASA's Infrared Telescope Facility, Mauna Kea, and the ESA's XMM Newton spacecraft. These observatories will study the star's radio, infrared, and X-ray emissions, respectively. What about two stars colliding? We have mentioned it briefly, but what really happens? Well, first off, star collisions often happen in the regions surrounding black holes, which you will find at the center of most galaxies. There is a vast cluster around a typical black hole where stars usually rotate, so they can't completely avoid bumping into one another. Star collision can occur at relatively slow speeds, and it will result in a merger. The resulting star is known as a blue straggler, which you can easily identify due to the immense brightness and hotness when compared to the other stars in the cluster. When stars collide at high speeds, the outcome is different. This type of collision is rare but is far more destructive. There is no merging here. Instead, there's an explosion. Also, the outcome of a stellar collision depends on the type of stars involved. For instance, as mentioned before, when two white dwarf stars that are part of a binary system collide with any other kind of star, it results in a Type 1a supernova. In this type of collision, gas is stripped from the more giant star and forms an accretion disk surrounding the white dwarf. Eventually, a critical mass is reached in the white dwarf and it explodes, ejecting what's left of the companion star into space. There is another stellar merger similar to the Type 1a supernova called a neutron star merger. This involves two neutron stars orbiting closely together due to gravitational radiation. Given enough time, they will merge to form either a more massive neutron star or black hole. Red giants do collide with neutron stars too, and this creates a strange hybrid star called a Thorne-Zeitkow object. This event usually only happens in the crowded environments of globular clusters. The red giant or supergiant ends up digesting the neutron star. The result is a red giant surrounding a neutron star core. The last of the main kinds of star collisions and mergers is the merger of binary stars. These are sometimes called contact binary systems. Binary systems are very common, but some pairs are more stable than others. Other binary pairs will be unstable and will eventually collide with each other. So how far away are the closest stars that can go supernova? A frequently talked about candidate for a supernova is Betelgeuse, one of the brightest stars in our sky, part of the famous constellation Orion. Betelgeuse is a supergiant star and is very brilliant. This star is due to explode one day. Betelgeuse's enormous energy requires that the fuel be expended quickly. Quickly here is relative though, but the fact is that Betelgeuse is now near the end of its lifetime. Someday soon, again soon here refers to space-time, which is vast, it will run out of fuel, collapse under its own weight, and then rebound in a spectacular Type 2 supernova explosion. When this happens, Betelgeuse will brighten enormously for a few weeks or months, perhaps as bright as the full moon and visible in broad daylight. Exactly when this will happen is anybody's guess. It could be in our lifetime or a million years away. It is like a ticking time bomb that could tick on forever from the human perspective. However, when it eventually happens, any beings on Earth will witness a spectacular event in the night sky, but earthly life won't be harmed. That's because Betelgeuse is safely 430 light-years away, so we can carry on with our activities without the dread of being wiped out by a supernova. And how often do we get to witness a supernova taking place within our own galaxy? Estimates vary, but they are all long periods. Some experts say at 15 million years intervals on average, while others put it at 240 million years. Meanwhile, did we mention that thermonuclear supernovae mean the complete destruction of a white dwarf star? Well, a new discovery is making scientists rethink that theory because they recently found a star that survived such an explosion. It not only survived, but it became even brighter. A team of researchers was examining the site of the thermonuclear supernova SN 2012Z using the Hubble Space Telescope. Actually, thermonuclear supernovae or Type 1a supernovae are important to astronomers because they use them to measure cosmic distances. They have helped to reveal that the universe is expanding at an accelerating rate. SN 2012Z was a strange type of thermonuclear explosion that is sometimes called a Type 1aX supernova. They are not as bright as the standard Type 1a. In fact, because they are less powerful and slower explosions, some scientists have suggested that they are Type 1a supernovae that did not succeed. Supernova 2012Z was detected in the nearby spiral galaxy NGC 1309. Hubble took images in 2013 in an attempt to identify which star in the older images corresponded to the star that had exploded. Analysis of this data in 2014 was successful. Scientists were able to identify the star at the exact position of the supernova 2012Z. It was the first time that the star that's responsible for a white dwarf supernova was identified. Why did the exploded star get brighter? The researchers suggest it was because the star puffed up to a much bigger state, so the supernova wasn't strong enough to blow away all the material, and some of it fell back into what is called a bound remnant. In time, the star should slowly return to its initial state, but it will be less massive and larger. So basically, nature attempted to strike this star down, but it came back more powerful than anyone could have imagined. It is still the same star, but back in a different form. It transcended death.